We use biological verbs to talk about artificial intelligence. We talk about training computers, learning tasks, and feeding data into systems. These metaphors suggest a human-like intuition that computers simply do not possess. Thinking of a machine as a digital pet obscures the actual computational mechanics at play. Beneath the metaphors, machine learning is a specialized subfield of artificial intelligence focused on mathematical simulation. It relies on one mechanical driving force: the use of algorithms designed strictly to automatically improve the performance of other algorithms. Machine intelligence is a cold, iterative process of mathematical optimization. To see how this works, consider a standard classification task, identifying whether a digitized photograph contains a cat. The machine views the problem as a mathematical structure called the model. It takes a grid of raw pixel numbers and transforms them through calculations into a new output, a label saying cat or not cat. In its untrained state, this mathematical shape is useless. It has the right structure for the task, but lacks the tuning to produce accurate results. Creating the model is just the first step. Generating reliable predictions requires a secondary, corrective mathematical force to refine it. That corrective force begins with the objective function. This coordinate plane measures failure. The objective function calculates the exact numerical distance between the model's guess and the correct result. A training algorithm then uses this distance to mathematically nudge the model's parameters, reducing the error. This process is entirely mindless. The algorithm has no concept of what a cat is. It only functions to minimize a numerical distance toward zero. The loop then restarts, processes another example, identifies the new distance, and nudges the parameters again. We call this learning, but it is actually the relentless, automated minimization of mathematical error until a reliable approximation of the task emerges. Our cat recognition example is a form of supervised learning, which depends on data that has been pre-labeled with the correct answers by humans. In unsupervised learning, the algorithm receives unlabeled data and must discover hidden structures on its own, eventually grouping similar data points into these geometric clusters. A third approach, reinforcement learning, is used for dynamic tasks like playing games or driving cars. Instead of following fixed examples, the model navigates an environment and receives a reward signal, optimizing its behavior to maximize points through trial and error. Regardless of the environment, the underlying engine is the same mindless loop of mathematical adjustment. When you apply this nudging loop to the massive architecture of artificial neural networks, you get systems like large language models. These deep networks contain trillions of parameters, all working simultaneously to predict the next word fragment in a sequence. This scale allows them to perform complex tasks that humans cannot explicitly program, creating models with immense predictive power. This graph shows a primary vulnerability of large models called overfitting. A model can become so focused on its training examples that it zigzags to hit every single point perfectly, losing the smooth trend line it needs to handle new, unfamiliar data. This mindless reliance on training data creates a second problem. Because the objective function treats the provided data as the absolute truth, it mathematically encodes any human biases or historical prejudices found in those examples into the model's parameters. This leads to the interpretability problem. Because the network built its own internal rules through billions of automated nudges, its creators cannot explain the exact logic behind its specific outputs. Human-like capability emerges purely from the relentless, unknowable complexity of